Hi, in this video we will see how we could tune a PID controller using gray wolf optimization. Now we previously already explained that any control system has two main components, which is the system and the controller. And we said that if you have the system and you have the transfer function of the system, and this is like the actual output of the system, which is y of t, and this is your desired output or the set point or the reference value that your system should follow. Now the error goes to the controller, and the controller generates the control law U, which is make the system perform as we would like. Now, and this is the feedback control system. We assume that our output is measured by a sensor. Now, the purpose of the controller is to keep the process output close to the desired value by using this control law. Now, we explain what the PID controller, and we say that it's very simple and it's available everywhere and it has a successful history. That's why PID is still considered as a very good controller. And it has three terms, which is the proportional, which is the KP just multiplied by the error, and the integral, KI, the tuning parameter KI or the gain, multiplied by the integrating of the error, and also the KD, the derivative part, which is we multiply the KD by the derivative of the error. So this is the control law of the PID controller, KPE of t plus KI, integral of the E, plus KD, the derivative of the E. Now, if the question is like this, we have a transfer function, and we need to design a PID controller for that system, and also we need to tune the PID using the gray wolf optimization. Now, just quick recap of the tuning and the optimization. Now, the key to design a PID controller is to find the right value of the adjusted parameter, which is the KP, the KI, the KD in the case of PID controller. Mostly, this tuning is being done by the trial and error. Just to try different number, different combination in order to find the response that satisfy what you want. Now, in order to overcome the drawback and the delay with using the trial and error, we try to formulate this tuning process as an optimization problem, and then we just have any optimization technique. We use it to solve the problem. Now, also like a fresh recap, what's about the optimization problem? Optimization problem in general is to find the best solution among all visible solutions. It has some terminology which is important when we design the optimization problem. So for example, you have to understand what the objective function, which is the function is desired to maximum and minimum. Now in our case, our objective function is to minimize the integral time of absolute error. This is one of the index that we use in order to optimize the PID controller to reduce the error between the actual output and the desired output. So the equation of this is the integral, and we multiply it by time and absolute the error. And there are so many other index could be used. Now the decision variable, also one of the most important terminology in the optimization problem, which is what's the parameter that the decision maker control. In our case, we have KP, KI, KD, three decision variable. We need to decide the quantity, the value of these variables in order to minimize our objective function. And also we need to know the search space, which is the search space of the KP, KI, and KD. Now, gray wolf optimization, this is the optimization that we will use in this video to optimize the PID controller. The gray wolf optimization is one of the meta-heuristic or swarm intelligence optimization technique. It's mimic the leadership hierarchy and hunting mechanism of the gray wolves in nature. The idea of hunting in the gray wolf is to divide the group of the wolves into four groups. The first, which is the alpha, they are the leaders. They have the highest knowledge and experience how to hunt. And then you have the beta, which is the subordinate. And then you have the delta, which is less have less information, and the remaining they call it omega. So in order to make a decision in the gray wolf, they share the alpha and beta and the deltas like they are the guide for the omega, the other wolves, in order to search for the hunting. Now the hunting process is in three processes: the searching process, enriching process, and then attacking. Now in order to design this algorithm, all you need is to understand that each wolf represents a possible solution. And you need to have a population, which is n of the all wolves that will be using the algorithm. We need to know the search space for all the possible solution. And also we need to guide the hunting process. The guidance is set by the best solution, which is alpha, then the second best solution, which is beta, and the third best solution, which is delta. So these are the three information that we need from the algorithm in order to guide the remaining of the wolves toward like the prey, or let's say the optimum value that we need in our algorithm. And also we need to have the component A, which is linearly decreased from 2 to 0 in each iteration. Now the procedure is in the following. The first is just you initialize the population by random value with the search space. So imagine that you have this population, and this is the xi, which is the position of your population, and you just randomly set different value to your population, and then you evaluate. So you take each value, you put it in your function, your cost function, and you evaluate this population. Then you will go to the update the population. In the beginning, we have to find the vector A, which could be found by this formula: 2 multiplied by A, which is A linearly decreasing from 2 to 0 in each iteration, and R1 is just random value minus R. And also we have to find C, which is 2 multiplied by random value, which is R. Then we have to design, we have to find the best alpha and the best beta and the delta. Now we said the alpha is the first best solution in our population. So in our case, if we go to this, which is our cost function, and we are looking for the minimum, so this is the minimum, and we consider this is x alpha. The second one is 0.5, which is the second best cost function, and it will become beta. And then delta will be 0.5, because the cost function of this 0.5 is 2. So 1 is x alpha, 4 is x beta, and delta is 0.5. Why? Because this has the first minimum, this is the second minimum, this is the third minimum. After we find x alpha, x beta, and x delta, we have to find the vector D. So D alpha, we just use the C1, and x alpha, which already found it, and x, which is our current position. And also in the same scenario, we find the B and the D for beta and D for alpha. After we find the D, we find x1 and x2 and x3. So x1 is based on the x alpha, A, and the D of alpha. x2 is x beta, A, and minus A multiplied by the D of beta, and the same thing for the x3. So if we found x1 and x2 with the x3, the next position is just the average of these three x's divided by 3. So the point here, the algorithm works in this way. We have 3 information, which is x alpha, x delta, x beta. We need to know the best next position for our current iteration based on this 3 information. So from A we find D, from D we find x1 and x2 and x3, which is like x1 related to the alpha, x2 related to the beta, x3 related to the delta. And after that, we just find the next position of our individual solution is just to sum all of these 3 divided by 3. And then we evaluate the population again to find the minimum. And if we get to the maximum iteration, we just stop and print the value. Now, what's the parameter that require from the user to set up the initial position, the population, sorry, and the initial position, the coefficient value A, and it's normally set 2, and it decreases with each iteration. And also you need to have R1 and R2, which is just random value between 0 and 1, and the termination, which is the maximum number of iteration. The pseudocode of gray wolf, first we put all this information, which is the cost function, the population, the coefficient A, and the number of iteration. And then we just go to the initialization. So we initialize the population, and then we evaluate. And we go to the loop. For each iteration, we find XA, XB, and X delta. And we go to each population. We calculate A and C and D alpha, D beta, and D gamma, D delta. And then we find X1, X2, X3. Update the position by using this rule. Evaluate the cost function. And it depends on the convergence or the iteration. And finally, we just print the solution. So this is the algorithm of the gray wolf. In our problem, our objective function is to minimize the error, the variable we have, the KP, the KI, KD. So let's go to the MATLAB to see how the code of this algorithm. In the beginning, we already know that CLC is to clear the common window, clear all to remove all the value, to clear the value of the variables, close all to close all the window. The simulation time, it's for our simulation for the control system. We just simulate it for 20 minutes. Now, the open loop of our system, you can see like here. So this is our system. So the coefficient is 1 and 2. And here the coefficient is 1 and 2, 3, 5. So this is the coefficient of numerator and denominator. And let's take in the beginning the system like stable. But let's see the response of the system. Now here we just divide the time by sampling time to 0.1. U is our step input, which is just 1. And Y, we simulate it by using LSIM, which is to simulate the output. And then we just plot the Y with the time. And we give just the X table the time, and Y is the amplitude. Now, if you just stop the algorithm here, so we just run the code. So we can see this is the response of our system. So your system is oscillation, and we need to improve this system. And also we could simulate the system if it's unstable. We just give minus here, and we just simulate. So we have two cases here. The system is unstable, and we want to see how the PID, if it's tuned by gray wolf optimization, how your system becomes stable after we apply PID controller and we tune it with the gray wolf optimization. Now let's go to the remaining of the code. T is the number of iteration, and I just put 10, so the algorithm will run fast. You could use like more than 10. Number of population is just 5. Number of variable is 3. You could see here that you don't have too much tuning parameter as a PSO or like ant colony optimization or even the flower pollination algorithm. So the good thing in gray wolf optimization, you don't have too much tuning parameter. We just consider the search space from 0 to 50, and this is up to you. And this is the counter for the simulation, and this is our reference value. And the first thing is the iteration. So we are now in the initialization. Now we are in the initialization. P is just a counter for the population. For each variable, like KP, KI, KD, we have 3. We set each one between the upper and lower limits. After we get the value, we just put it in the PID controller. So the KP is the first one, the KI is the second one, the KD is the third one of each population. So of each individual in the population. Now we simulated the model. We first built the transfer function of the PID controller. So we use the code PID, which is already in the MATLAB. So PID, KP, KI, KD. And then we use the closed loop. We use the G closed loop, which is just feedback. So this is the controller and this is the open loop. So if we go here, we will see that the controller is multiplied by our system, and then it's feedback, like unity feedback. So here is your controller multiplied by your open loop system, and then we take it feedback, unity feedback, and then we simulate the output. So this is the one, which is our step input, and here we just simulate the output as a closed loop. And here we just calculate the objective function. So our objective function, as we decided here, we consider the objective function is integral absolute of the error. So we just multiply. So this is the absolute of the error. We just must subtract your output from your reference, which is 1, and we take the absolute and the summation, because we do integral, and just multiply by the time. So this is our cost function. Now we have different objective function for each population, for the number of population. Now we just take the minimum as the best value from the initialization. So here we just take the best value, and here we take the position, which is Kp, Ki, Kd. Now we go to the iteration. In the iteration, the first stage is to calculate the A. So if we go to the optimization, we said that after you initialize and you evaluate, then you start find the A. So the A is the coefficient capital A is depend on the coefficient small a. Small a is reduced, as we said, is reduced with each iteration. So this is the formula for small a. So they are reduced, the a small is reduced with each iteration. Now we need to find, as we said, we need to find the alpha and beta and delta. We need to find which is x alpha and x beta and x alpha, x delta. Now we first take all the objective function we have, and we take all the x. So it's like we take all the objective function and we take all the x, which is the population, and then we ask for the minimum. Which is the minimum? So for example, this is the minimum. This is the minimum cost function. So we take the x as alpha. So we take the position alpha, which is the position, and we take it as a cost function. So this is the x alpha. Alpha slash var, this one is how we find the x alpha. Now we have to remove it from the population. So we remove x alpha from the population, and then we take the minimum again. So here we removed from the objective function, here we remove it from the population, and then we find the minimum again. So if we remove this one, we remove this one. So what's the minimum? This is the minimum, and it will be the x beta. So after we delete the minimum, the first minimum, we find the second minimum, which will be the beta. So this is the objective of the beta, and this is the variable, the x beta. And then we will delete. So we will delete beta again, and we ask what's the minimum? So the minimum is 2, and the x which find 2 is the x delta. So here we just remove the beta, and then we find x delta. So from here we already find x alpha and x beta and x delta in this stage. Then here we find c and a, which is here. We just calculate a and c, the coefficient a and c, and I said is just a and 2 multiplied by a random value minus 1, and the c is just 2 multiplied by the random value r. So after we find c and a, with each iteration, with each variable, we just find the d and the x1. So the d for alpha and x1, the d for beta and x2, the d for delta and x3, and the new x is just sum of these three x's multiplied by divided by 3. And then we check the convergence, we check the search space. So we should ensure that the new position is within the search space. And after we finish, we just go to run the system again. So Kp, Ki, Kd, which is the x1 and x2 and x3. And then we just put the PID controller, the feedback system, and we simulate the step, and we find the y. And here we just find the cost function again. After we find the cost function, we take the minimum. So we just compare our first minimum from the initialization with the new minimum. So if we find something good, we just take it as the first one. If it's not, we just keep the first minimum that we found by the algorithm. And here we just plot with each iteration. We just plot the cost function with each iteration, and finally we just simulate the final response of the system. So here we just print the best cost function we found. Here we print the Kp, Ki, Kd, and here we simulate the last version of the system with the Kp, Ki, Kd, which is the best one we found by the algorithm, and here we just plot it. So let's run the code and see how the gray wolf will tune the PID to improve the performance of the system. Now we will take the two cases. The first case, which is the system is stable but has oscillation, and when it is not stable. Now, as you can see, because we just don't take too much iteration and not too much population, so it's just to see this is the convergence. So we start from like 1.02 and we just get down to the 0.9. So this is the convergence, which is the error, how the error is reduced with each iteration. And this is the response of the system without controller, and here is the response of the system with the controller. You can see the difference, how the PID improve the performance of the system, and also the system is the settling time is good, and the overshoot is also good. And again, you could improve the performance by changing the performance of the system, like by increase the iteration, the population, the search space. Now we could try different case, which is when the system is non-linear. Sorry, when the system is not stable. Now let's run the code. Now again, we check. So this is the convergence of the system. Look, the error was high and then it get down. And also we could check how the system was unstable and then it's become stable with the PID controller. And we could see here from here, so the value of KP and KD and KI, and also we could find the minimum of our index. So this is all about how we tune the PID controller using Gray Wolf algorithm. See you next time. Thank you.